Hello everyone and welcome to yet another math video. In this video I will be going over function basics. So for one of the first things you learn about functions and relations, which are just functions that aren't functions, is you learn to identify whether or not what you're looking at is a function. So I'm asking the question, which of the following represents a function? If it is not a function, explain how you know it isn't. So with part A, you can see here we have a set of ordered pairs, and really what we're doing is we are comparing all of these x values, and we're just trying to see if any x's repeat. So I see 4, 3, 2, 8, no x values repeat, so this is a function. And that's all we need to know, that it is a function. I only ask that you explain if it's not a function when it isn't. Okay, next example here, part B. I've got 5, -3, -2, -3. So part B is not a function, and the offending x value is -3. Repeats in the x coordinate. And that's how you work with a set of ordered pairs. Now for the graphs for parts C, D, and E, you can see pretty clearly that some of these will or one of these won't be a function. So for part C, I'm going to go ahead and just let the cat out of the bag that this is not a function. And the reason is, and this is how I expect my students to show work, it fails the vertical line test. That means there is at least one vertical line that passes through the graph more than once. So say this left vertical line, that passes through the graph more than once. The graph being this top curve here, and additionally at the same time this bottom curve. But not only that, all of these vertical lines cross more than once, right? We just need one, but since we found one, it could have been any one of these lines. That's what makes it not a function. And how I say it is it fails the VLT, which stands for the vertical line test. All right. Let's look at part D. If you make a bunch of vertical lines here, none of these pass through the graph more than once, so this is a function. So we don't need to explain why, but there's the work shown up here. And lastly, here with a different color, this part E is also a function because it passes the vertical line test. Continuing with function basics, I will explain how to evaluate functions given the function equation. So here we call this function notation. The g is the name of the function and x is the variable that will be used on the other side of the equation. So we have g of x equals -2x squared plus x plus 6. So what you need to do in order to evaluate a function is a couple different things. One is recognize that the x here is replaced by a number. So when we work this out down here for part A, say g of 0, that means all of the x's will get replaced with this 0. So I'm going to write this out like this to begin with so I can hopefully make this be clear, is that there used to be an x here, now it is 0, which means there used to be x's here, which you can see by these parentheses, which will become 0. And you can simplify all of this down to become 6. So we can write g of 0 equals 6, and that this is an x value and this is a y value. Another quick thing to point out is that when your input, aka x value, is a number, then your output, aka y value, will also be a number. Moving on, parts B and C, you can do for yourself. Just make sure you're keeping track of your signs. You're using parentheses around the values you substitute in for x. I want to jump down to example D. So here, D, we have g of p. So one thing I want to point out here is that p is the variable that will be used on the other side of the equation. So we have g, that's the function name. We know to use this function here of p. Then x was replaced with p, which means all of these other x's should be replaced with p. And again, I'm just using parentheses here to set it up because these x's in the original equation will be replaced with whatever x was replaced with, in this case, p. So I've got negative 2p squared plus p plus 6. And this makes sense because way back at the beginning of this slide, I said whatever is in the parentheses is the variable used on the other side of the equation. Still holds true. All right, let's take a look at part E, where we find g of x plus 1. So what that means again is that x was replaced with x plus 1. And I want to go over a very specific part of this. So this will equal negative 2 times x plus 1 squared plus x plus 1 plus 6. Now, this is the first step. There's a lot of simplifying that needs to happen here. So just off to the side, or in this case below, I'm going to do a little bit of scratch work for this portion of this. Take the time, write it out, x plus 1 times another x plus 1, and distribute it all out. So you can do x times x times 1, 1 times x, 1 times 1, and eventually it becomes x squared plus 2x plus 1 when all is said and done and simplified. So the only piece that we figured out so far was this. It becomes x squared plus 2x plus 1. Everything else comes along for the ride. So I have equals negative 2 times that plus x plus 1 plus 6. Then you can see to make the distribution here and get negative 2x squared minus 4x minus 2 plus x plus 1 plus 6. And then combining any and all like terms that you're allowed, minus 2x squared minus 3x plus 5. So there's the answer for part E. And I'll take a look at part F on the next slide. For part F, we are supposed to find x, so we're trying to solve for x here. So g of x equals 5. Remember that function notation just takes the place of y, so if it helps, you can think of it like that. We're just replacing this y value with a 5, and then solving the resulting quadratic equation. So one thing that happens here before I get too far into solving is that you want to try to make sure the a value is positive, and right now it's negative. So instead of just subtracting 5 from both sides, I'm going to add 2x squared and subtract x and subtract 6, all from the left side, so I can get a 0 over here. But that resulting equation would be 2x squared minus x minus 1. This factors, or you may have to use the quadratic formula in some cases, but since this factors, I'm going to go ahead and do that factoring. This is 2x plus 1 and x minus 1. And then we can set each of these equal to 0 and solve for x to get x equals -1/2 and x equals +1. And these are the two answers that if you substitute them back into the original function, will give you a y value of 5. Taking a further deep dive into function basics, sometimes we get these functions that look like they are made up of multiple pieces. This is called a piecewise function, and really the big noticeable obvious reason this is in multiple pieces is because you can see the multiple pieces here. The negative absolute value of x plus 2 and the negative 2x plus 3. Now, we can't just go substituting numbers in for all the x's here. We have to pick a piece and stick with it. So you might also notice these inequalities that are hanging around back here. And this is just one way to notate it. Instead of a comma, there might be the word if or when sandwiched in here between the function and these inequalities. You just have to be flexible with it. But these inequalities serve the purpose of helping you pick which piece to use. So say, for example, part A, we have g of -1. You can't just substitute -1 in for both of these x's and get two answers. This is a function after all. We can't substitute one x value in and get back two y values. That is exactly what makes a mathematical equation not a function. So which piece do we use? We just compare this x value, right? That's used to be an x, now it's a -1, so this is an x value with these inequalities. So where does -1 go in these inequalities here? Well, it looks like this bottom one, because -1 is in fact greater than or equal to -1. So for this, I normally number the top one 1 and the bottom one 2, and I'll say we need to use piece number 2, which means we can substitute in, this is -2 times -1 plus 3. And you can simplify that down to get an answer of 5. But remember, we had to use these inequalities to pick which piece to use. So for the next example, part B, if we look at g of 2, well, where does 2 go in these inequalities that makes sense? Is 2 less than -1? No, but 2 is greater than -1. So again here, we will use equation number 2, or piece number 2. And this will be -2 times the 2 that is the x value now, plus 3, which is -1. Part C, here we have g of -5. So we just do our comparison again. Is -5 less than -1? Yes. So in this case, we will use the top equation, and we just substitute the -5 in for x. Simplify what's inside the absolute value to get a negative absolute value of -3. And then, of course, the absolute value turns any number into a positive number, but that negative in front is still there. So the answer here ends up being -3. On this slide, we will go over how to find the domain for each of the following functions in interval notation. There are a couple things that I teach here in that this early in a course, we only look at square root and rational functions that restrict domains. So I can clearly see that part A is a square root, and part D, E, and F are all rational functions. And all that means is that there's a variable in the denominator that is not inside of a square root, or additionally has whole number exponents. So part B is a cube root, and part C is what we call a polynomial or a quadratic. And both of these, right off the bat, since there are no x's in a square root or in a denominator, these both have all real numbers for the domain. To review how to find the domain for a square root function, for part A, you can take the inside only of the square root and set it to be greater than or equal to 0 and solve for x, in this case by subtracting 4. That leaves you with a minus x is greater than or equal to minus 4, and then dividing by a -1 to cancel out that negative. But when you do that, again, when you divide by a negative, only by a negative, that leaves you with an x and a 4, but the inequality sign changes directions. And then however you can get this over into any interval notation, it's going to be -infinity to 4. The 4 will have a square bracket around it because of the equal to here, and then infinity will always have parentheses. So that's the answer for part A. Part B, I'll put here. When you see a variable in the denominator, what you will do is you will take the denominator, in this case x, sorry, not part B, part D, there we go, and it will be x minus 5 in the denominator not equal to 0, which means x cannot equal 5. And even further, what that means is that numbers less than 5 work because they are not equal to 5, and numbers greater than 5 work because they are not equal to 5. So that means in interval notation, we can pick literally any number less than 5, and we'll use parentheses around it because not equal to means excluded. But there will be a second interval because any number greater than 5 works as well. And then you will join those intervals together with a union like this. I will work through part E and F on the next slide. For the final two domain questions from the previous slide, I've already taken the denominators because I remembered they have denominators, and set them not equal to 0. So these will be solved similarly, but have two very different outcomes. So for this first one, part E, I see this can be solved using the square root property. So I'm going to use the square root property here to solve this by adding the constant to both sides and say x squared cannot equal 36. Then I'll take the square root of both sides, not forgetting the plus or minus in front of the square root with the number. That cancels the square, and it says x cannot equal 6 or -6. Now I will draw out a graph for this one just to do it. So there's -6, there's 6. Make sure your numbers are in order if you do this. Not equal to means using open dots, and we can shade everything between, to the right and to the left. From there, we can create the intervals. So you can almost think of it like these open dots is what will create the unions. And you can see that it'll be -infinity to -6, -6 to 6, and then 6 to infinity. Now, this finding the domain technique could be used with quadratics that are 3 terms as well. And if you see a denominator with 3 terms, you will most likely be factoring instead of using the quadratic, the square root property. Now for part F, we're just going to follow the similar process. We're going to use the square root property. So x squared cannot equal -25. Take the square root of both sides. Don't forget your plus or minus in front of the number. That leaves you with x cannot equal plus or minus 5i. And what this is telling you is that x cannot equal an imaginary value. And that's fine. Like, so you're not telling this is not telling us anything that we don't already know. when we're finding the domains, we need to work with real values, not imaginary values. So the fact that it cannot equal an imaginary value is moot. It doesn't make any sense for us to say out loud even. So what that means is the domain is negative infinity to infinity because there aren't even imaginary values to remove from a number line. So these are the two answers for part E and F. To round out the function basics review here, we will just look at a bunch of different characteristics for the graph on the right. So use the graph of f of x on the right to find the domain of f. So to find the domain from a graph, not from a function like the previous couple slides, that will go negative to positive in the x direction, in this case left to right. So this arrow is pointing completely left forever, so we know the domain here will start at negative infinity, and this arrow on the right side of the graph goes right forever. So what that means is that it will go all the way over to positive infinity. Okay, so the range is similar to the domain in the fact that we will start negative and go positive, but the range are all the possible y values. So that means we'll start at the bottom of the graph and work our way up. Now this graph can be a little misleading because students will think, well, this graph starts at -3, and that is correct. So let's go ahead and put that there. It starts at -3. But then students will follow the graph up and say, this left side goes higher than this right side, and they will try to stop the range at +3. But that's not what happens. The range actually goes off to positive infinity because this arrow points upward forever. So make sure you're looking out for those arrows as you're going through and doing this. Regarding parts C, D, and E for increasing, decreasing, and constant respectively, what you are basically going to report are little domains. So we just found the domain up here, and you know that's going to be left to right. So what we have to do is identify on the graph what is happening here. So as the graph moves from left to right, I can see that it starts out constant or flat. And at this point right here, it changes. So it goes from being constant to being decreasing, aka it's going down left to right. So since there was a change, I'm going to notate this down to the x-axis so I know that something happens at the x value -2. Now if you follow the decreasing portion here, you can see we come to another point, and afterward it changes again. So it goes from decreasing to increasing, and that change is important. So I'm going to notate that by drawing a line up to the x-axis. I'm always going to the x-axis because these are domains, little tiny baby pieces of the domain. And then afterward, I can see that this graph is increasing. So one other thing I like to do here is just write what is happening. A C on the x-axis because it's constant there, a D on the x-axis because it's decreasing there, and an I on the x-axis because it's increasing there. And I keep referencing the x-axis because these are pieces of the domain. So where's this graph constant? Well, it starts left forever constant, and then it stops at -2. So for constant, that was part E. It goes from -infinity to -2. From there, the decreasing, which is part D, runs from -2 to +1. And then from there, it runs increasing from 1 to infinity. Now, I've not put any grouping symbols around these because I teach that when you're regarding or finding intervals for increasing, decreasing constant, I always use parentheses. So big distinction for domain and range. If a number is included and starts or ends a domain or range, use square brackets. For increasing, decreasing constant, always using parentheses. Okay, let me get rid of all of this stuff over here. Let's move on to parts F and G. Now, you know that, of course, X is what's normally in the set of parentheses here, but when it gets replaced with a number, that's the new X value. So X value here being -3, what you should be thinking is finding this number on the X-axis. So -3 on the X-axis right there. And then what you'll do is you will follow the graph either up or down, or you'll follow up or down to get to the graph. So right now, I'm going to go up, and that is the point on the graph that has an X value of -3. The Y value paired with it is +3, so this answer will be 3. And you can do something very similar to find out that the Y value paired up with the X value of 2 is -2. Now, for parts H and I, there's a different way to go about it. If you'll remember, f of x is the same thing as y, so we know the y value this time, and the y value here is +1, so we're going to find 1 on the y-axis, and since we're looking for x's, I think it makes sense that we need to go left or right to find those x values. And make sure you're looking both directions because there are 2 points here. This is -1, 1, and you can see that that y value is 1, and that's what we were looking for. And this other point over here is 5, 1, and you can see again that that y value is the one we're looking for. So 1, 1. So what are the x values paired up with that? Well, we have an x equal to -1 and 5. So there's the answer for that. And you can do something very similar to figure out that part I would be x equals 1. Now this last example, is it even, odd, or neither? How can you tell? An even graph is a mirror image around the y-axis. Let me clear this stuff here real quick. There we go. So it would be a mirror image around the y-axis, which means we'd maybe have to see something like this in order for it to mirror this. That's what would make it, even. Or if we were looking at the left side of the graph, it would have to look like this in order for it to be even. But that's not what the graph is, so we can say that it is not even. In fact, is it odd? Well, in order to tell that it's odd, you'd have to picture this graph flipped upside down. And for right now, if you turn your head as best you can, this graph will not be the same graph right side up and upside down. So it's not odd, which means this graph is neither. It's neither even nor odd. How can you tell? No symmetry to the y-axis. That would be even, or origin. That would be odd. And that finishes the content for this video. I hope it helped out. See you in the next one.